Dear students of B Tech first year, I am Dr. Rohin Parsai, Associate Professor of Mathematics in Engineering and Humanity Department at Chamini Devi Group of Institution Indore. I wish to teach you through lecture 4, Introduction of Series Solution of Second Order Linear Differential Equations with Variable Coefficient, and I also discuss the working procedure for power series solution around an ordinary point or regular point with example. So first of all, we understand what do mean by power series solution. For that, first we understand what do mean by power series. It is an infinite expansion is of the type as summation m equal to 0 to infinity m x minus x0 raised to m. If you open the summation sign for m equal to 0, so you will put here, this gives to you power is 1, so a0, then you are getting the second term when you put m equal to 1, and so on, where a0, a1, and these all are the constant coefficients, and x0 is a constant which we called as center. Now, what do mean by series solution? In general, the solutions to differential equations with variable coefficient such as Bessel's equation, Legendre's equation, and hypergeometric equation cannot be expressed as finite linear combination of known elementary functions. However, in such cases, solutions can be obtained in the form of infinite power series. In this section, two methods, power series method and extension of power series method, the Frobenius method, generalized power series method, are considered. So let we understand first of all which type of differential equation we face here. So we have the differential equation is of the type p0 of x d2 by dx square plus p1 of x divided by dx plus p2 of x of y equal to 0, where p0 of x is non-zero. Then first method is solution around the ordinary point or regular point. So for this, a point x0 belongs to I set of integers is said to be an ordinary point of the equation 1 if p0 of x0 is not equal to 0. And the second category is the regular singular point. A point x0 belongs to I set of integers is said to be regular singular point of the equation 1 if p0 of x0 equal to 0. So when the coefficient of the second order derivative is vanishes, then it is the case of regular singular point, and when it is not vanish, it is the case of ordinary point or regular point simply. So let we come to understand the working procedure for finding power series solution when x equal to 0. Say x equal to 0 is an ordinary point or regular point of the equation 1. So that is when p0 of x is non-zero for x equal to 0. So in this case, we assume the series solution in the pattern as summation k equal to 0 to infinity akx raised to power k, that is equal to a0 plus a1 of x plus a2 of x square. When you open this summation for k equal to 0 to infinity, you will get this is an infinite expansion as a series. So be a solution of given equation, call it by 2. Then to find the values of these coefficients, so now our objective is to find the values of these coefficients. For this, we are using just the concept of solution. So what do you mean by solution of an equation? When the equation is satisfied by it. So that's why we need first derivatives and second derivatives. So first we differentiate this equation number 2 with respect to x. So this gives to you first term vanishes because it is a constant. You will get, so that this summation starts from 1 k equal to 1 to infinity k into a k x raised to k minus 1. So the differential is this. When you continue again, second time when you differentiate, so then the second time is also vanish. Therefore that is the summation start from the third term. For third term, k ranging from k equal to 2 to infinity k into k minus 1 a k into x k power k minus 2, the differential of this second time here. So this is first differential. When you again differentiate, you will get this expression here. Now on substituting this value of y divided by dx and dy by dx square in equation number 1 and then equate to 0, because right hand side of the equation is 0 to 0 of the various powers of x, and then so that we get a2, a3, a4 and so on in terms of the two constants independently, a0 and a1. So out of these infinite constants, two of them to be independent, because we are having second order differential equation. If it is third order differential equation, then 3 out of these infinite constant, 3 will be independent here. And now therefore on substituting these coefficient in equation number 2, you will get the series solution or power series solution having a0, a1 as arbitrary constant of the given equation. So now the very important note for solving this category of problems as method number 1 is equate to 0 the coefficient of x power n. The relations to obtain is called the reconciliation. Give different values to n in the reconciliation to determine various ai's in terms of a0 and a1. Now this method, above method, is well explained by the example. Let me understand an example. So the question is asked the way is find the series solution of the following differential equation as y double dash plus y equal to 0. So our step is to check it whether this differential equation shows an ordinary point or regular point just by putting the coefficient of second order derivative to x equal to 0. So here this is not to be vanished. So that is the case of 1 as first case. So that's why we know that in this case we assume this series solution in the pattern as y equal to sigma m equal to 0 to infinity am x to the power m. Then you differentiate first time, that is this gives to you this differentiation when you differentiate first time. So x to the power m का differentiation होगा m into m x to the power m minus 1. When you open this summation you will get this. When you differentiate second times you will get this value here. So m into m minus 1 m of x to the power m minus 2. Now since your equation is this, just on putting this equation, these values in this given equation, and so this is the value of first term and this is the term value of y, and then on collecting the like terms here, first constant terms you are having the value of constant term 2a2 plus a0 and the terms having x 6a3 plus a1 and the x square terms and so on. You can continue this way. So now since 1 and x square and x to the power n are linearly independent functions, so their coefficients are to be vanished. So first equating the constant term coefficient, that the coefficient of x to the power 0. So this gives to you twice a2 plus a0 equal to 0. Then you equate the coefficient of x to the power 1, you will get this. When you equate the coefficient of x square, you will get this, and so on. We can continue this. So therefore obtaining these values from the above equations, a2, a4, a6 can be expressed in terms of a0, and a3, a5, a7 can be expressed in terms of a1, and where a0 and a1 are arbitrary constant. So after solving the above simultaneous equations, we get a2 equal to a minus a0 upon 2. Then you are getting a3 equal to minus of a1 upon 6. So that is, do you write in a factorial notation here? 6 can be written as 3 into 2 into 1, that is factorial 3, the value of this. Then you come to for a4 here, a4 is a0 upon factorial 4, and so on. You can continue this as substituting in the equation number 2, and by collecting the terms having coefficient a0 and terms having a1, so we will get the series solution in this pattern here. Now this terms, this belongs to cosine series, and this belongs to having odd powers terms having the sine terms. So that's why you can write in compact form this series solution a0 cos of x plus a1 of sin x, where a0 and a1 be the arbitrary constants. Since every linear differential equation with constant coefficient always possesses a valid series solution, it is natural to expect the linear differential equations with variable coefficient to have series solution too. Thanks for this session.